Hello, everybody. Hi. How are you guys doing? I'm Jamie. I've tried to mix and mingle and say hello to as many of you as I can. Welcome to the new faces. Hello to familiar faces. We're at FanDuel. Obviously, Oh, I should hold the mic up. We're live on YouTube, which is what this mic is for. Yeah, we've moved to FanDuel. Code Clan shut down for a short while, which made us panic. And thank you to the FanDuel team for stepping up. We really appreciate it, particularly Sasha, Robin, Ali, and Nick, who helped us get this venue kind of at the last minute and deal with me being worried about it since I was away up a hill, you know, when the news came through and was like, oh, you know, something else to sort out. So yeah, so really good space, and thank you very much to them. Thank you to KPV Lab for sponsoring the pizza tonight. We really appreciate that. If you don't know who they are, then check out the website and there's a link to KPV. They do some really cool data viz stuff, and you might have seen their previous talks at the last few meetups. Tonight, we've got two talks. We've got a very short talk from Alan, who does the live streaming with his new company left here with some lovely branding just set up. And he's going to do a talk on kind of audio file formats, and then we'll hear from Ross about generating noise and sound in JavaScript. Tonight, I will be drawing names out of a hat for a license for QuokkaJS and WallabyJS. They messaged me and said that they were happy to give away some licenses to the group. We're obviously now big enough to have attracted some attention online on the Twitter account, which is really good. So they are basically in-editor tools that give you feedback on testing and kind of execute JavaScript as you go to kind of give you feedback as you're typing. So I will be drawing names out of a hat at some point during Ross's talk and announcing that later on at the end of the evening, so stick around for that. I have put on the website a little bit of a feedback form. So if you go to EdinburghJS.org, there should be a link there for like attendee feedback. What I'm looking for is, I'm thinking about running a little weekend hackathon or like a single day hackathon or an evening hackathon around building a personal website. A lot of people who were at Code Clan have messaged me saying, how did you get a job? You know, like, do you have any jobs? And I think, you know, I don't particularly know how to get a job because I'm a freelancer and not got a job in quite a long time. But I do know how to make personal websites. And I think for very entry-level people who are doing particularly in front-end stuff, it is actually useful to have a personal website. So I was thinking about maybe doing a full day where I can sit down with people, chat through, you know, using a framework to kind of get something up and running quickly, and we can kind of collaborate and give each other feedback on what we've built. So if you're interested in that, fill out the attendee feedback and let me know kind of what your preference would be, whether an evening, weekend, or online. I'd really appreciate that. There's also a space for just feedback about the event. So please do fill that out. Want to try and make sure we're scheduling talks that are good for people. So without further ado, Alan, we're going to switch now, and I'm probably going to take care of the cameras. You ready?
Yes.
Right, Alan was.
No, Jamie, you keep that. Yeah. Hi everyone. For everyone who's extremely privileged to have heard me talk before, you'll know that I generally don't talk about JavaScript. This is no exception because I don't really know anything about JavaScript. And the reason I'm talking is because we need to fill out the speakers for tonight. So that's your hint for if you would be interested in speaking in the future. Actually, Jamie and I were talking, we're coming up with a new scheme where if you don't feel like speaking yourself and you'd like to nominate someone, a friend or a colleague to speak, just send us their headshot and a summary of what you would like them to talk about. And what we'll do is we'll just go ahead and put that up on the website, and then closer to the event, we'll just, you know, insinuate that they agreed. And actually, to be honest, they probably don't need to be a friend for that to work. So this is a talk about audio files, not these kind of audio files. These are the kind of audio files that like to spend too much money on HDMI cables. So this is the kind of audio file. Note the difference in spelling file there. Okay, this is a really deep talk, by the way. So this is what I'm going to be talking about. I just want to provide a little bit of tech stuff around digital audio to lead into Ross's talk, which is going to be far more coherent than this, I'm sure. this is an audio file HDMI cable. I think this costs about £200, £300. You can see here the gold-plated, no, that doesn't work, the gold-plated connectors for increased fidelity, audio fidelity. So Denon, if you're interested in audio stuff. So I think there's no point in talking about audio without explaining a little bit about sound first. So what is sound? Sound is molecules vibrating. So now that we've got a good theoretical understanding of the physics behind sound, let's talk about digital audio and how we represent that in a file. So there's a few things I'm going to cover, some basic concepts around how this works and some different file types. I'm going to rattle through this quickly. So the things I want to talk about are sample rates, bit depth, and bit rate. We get a quick show of hands. Who here in the room feels like, I'm confident, I know what all this stuff means? Okay, that's good. There's not too many audio files then. That's great. So if I make any mistakes, you're not going to have a clue that I've made a mistake here. So first thing is, we're going to talk about sample rate, which is, so if you imagine this screen right now is displaying a picture to you. It's not moving. I should have put an animated GIF here. That would have explained it a little bit better. But this screen is flashing 25 times a second, and it creates an illusion of movement. 25 frames a second is enough with the after effect in your eyes to look like smooth movement. Anything down to 24 frames a second, which is 24 hertz, looks absolutely fine to your eyes. To your ears, though, needed a bit more fidelity than that. So a CD, CD-ROMs for those back in the 90s, we sample audio 44,000 times every second. So that is known as sample rate. And there's different sample rates for different kind of audio. That's a sort of a standard one. And a thing I'll come back to is that the maximum frequency, audio frequency, and I'll explain what that is, that can be represented in a digital audio file is half of the sample rate. Now that might seem really weird, but I'll explain why that is. The second thing is the bit depth. Now, so basically what we're doing is 44,000 times a second, we are taking a snapshot of what the audio sounds like. And then what does that look like? What is that snapshot? Well, it is basically just the loudness at that particular time. So I really wish this would work. Do you see this? Anyway, so this is time from left to right here. And at this, so you can sort of see that there's sort of, it's kind of like there's a particular bar there. Am I making sense here? So at that particular point, it was that loud, and this point it was that loud, and it was at this point it was that loud, and on we go. So that is essentially us. If you imagine that was 1 second, and there's 44,000 of these little lines, which there's not, but just imagine. And that is our sample rate. Our bit depth is the range of values from 0, imagine this is 0 here, all the way up to how high this line can go. So I'm going to go to the next graph here, so this explains it a little bit better. So that's from left to right. And imagine each of these are one of those lines. So that line would be like that, and then a bit higher, and a bit higher, and a bit higher. So we can only go from 0 to 16. Can a techie person in the room tell me how many bits that is, and what the bit depth would be for that? 4. Yes, 4 bits. But we're going a little bit more than that with audio. Minimum, we're probably doing 16 bits, which is how many values? 5,300. He wins a prize. 24 bits? Right, and then 32 bits is a very, very big number. So modern audio files will do what's called 32-bit float, which is such a range of values that you're never going to run out of values. So that is what that is. So weird thing, though, is we've gone from left to right, and we've sampled the loudness. Can I get a volunteer in the room who can make a noise for me? Put your hand up. Jamie, excellent. Jamie, can you give me a sound that is loud and high? And a sound that is loud and low? And a sound that is quiet and low? And a sound that is quiet and high? I was really just trying to noise Jamie out there. So you can see there's a bit more to all of this than just loudness, right? So how is it that this can represent a sound in a room, which has got lots and lots of different audio frequencies present in it? So some high sounds, some low sounds, some loud sounds, some quiet sounds. All this is doing is sampling whether something is loud or whether something is quiet. So I'm gonna come back to that in a second. I'm going to show you this as well. So the next thing is, so we've got a sample rate, how many times a second we're taking that snapshot, and then the bit depth, of the range of values that we are able to deal with. The next thing is, so what does that range of values represent? They represent decibels. Decibels are kind of confusing. Decibels is a logarithmic scale. I'm not really going to. So what that means basically is if one sound is 2 decibels and another sound is 4 decibels, you can't just add them up to say 6 decibels is going to be this loud quite as easily as that, because it is a logarithmic scale. I've explained that so badly. But basically, when you look at a graph like this, so this is very hard to see, I apologize. But this is extremely loud up here, and this is extremely quiet down here. So there's a difference in loudness here compared to here on this scale. You notice the 10 to 15 and then 10 to 2 there. I'm not very satisfied with that explanation, but just nod and pretend that you understood that.
The best thing with logarithmic scale is the number of times you multiply. So, if you go 2, 4, 8, 16, it's the number of multiples of 2.
Yes, what Jan said. Jan said there. Thank you very much. Now, so there's been a few ways we've looked at how this is represented from left to right, and loudness here. This is the waveform from left to right, and loudness here. And this representation will be exactly the same from left to right and loudness. But you notice there's something else in the background here. This kind of, this orange stuff in the background. So that's, so we call this blue bit the waveform. And you've probably seen that, and you've probably seen it if you've used, Winamp or something like this. You've seen like these dodgy visualizations of audio. This orange bit is a spectrum analysis. So all this is telling you is whether something is loud or quiet. And that is when it's on the line and it's basically silent. And when it's all the way up here, it is extremely loud. Now, when I talked about the bit depth, this is definitely going all over the place here, from 16-bit, 24-bit, and all the rest of it. What happens if you exceed the value that you're able to store? You get clipping, and you basically don't get any useful information stored anymore. So that's why it's important that your sound can be represented in the range of values that you've got available to you. Okay, so this thing, spectrum analysis here. So you can see here, this scale is for the waveform. This scale is for the frequency. So very low frequency, Jamie? Yeah, and very high frequency, Jamie? Yeah. It's another way of looking at it. So very low frequency, very high frequency, and very low frequencies. So I think human hearing is about 20 hertz. So that's a wave that repeats over 20 times a second, all the way up to 20,000 hertz. That's the highest that you can hear. And coincidentally, we're at the CD. Remember I said maximum frequency that can be represented is half the sample rate. So 44 kilohertz, which is up to about 22,000 hertz is what a CD can represent, which is the threshold of human hearing. Okay, so right, let's go. Very cool, right? So how do we, if we're just storing time and values, how do we get from that to the spectrum analysis? Now, I'm not really going to properly explain this. I'm just going to tell you there's a magic Dos Machina solution to this called a Fourier transform. No, not that. Fourier transform, sorry. And what that does is let you take that waveform and split that out into the separate frequencies. And what it does is it takes some of the time information, from the information from left to right, and use that to reconstruct the various frequencies at a point in time. It's really fascinating stuff. I definitely recommend seeing some YouTube videos about it because Fourier transforms are used in all sorts of things. The reason I said I'm not going to try and attempt an explanation is because everyone will be out at me. The audiophiles, the software engineers, the data scientists, this is all kind of stuff that they do, and everyone's going to tell me, you made a mistake, that's not quite right, blah, blah, blah. Nightmare, who needs that in their life? So I'm not going to attempt to explain that. So all the stuff I've talked about here, the sample rate, the bit depth, is all relevant to what's known as, is relevant to how sound is generally stored in a WAV file, which is an uncompressed audio file. And it's basically from left to right, a particular sample point. This is how loud something is, how quiet something is, and that's all that WAV file has got inside it. There's no compression going on. We have some audio files which are compressed, and it's just taking that same data and squishing it down using whatever means that they can find to do it. And then we have lossy compression, which will take that information and chuck some of it away. So for instance, we talked about the fact that human hearing only goes up to 20,000 kilohertz. So actually, some MP3 compression might say, well, to be honest, most people can't hear above 18,000, so we're going to chuck away all of the top end. And a lot of people will be able to hear a lot of the bottom end, so we're going to chuck away some of that. And these values are kind of similar to these other values, so we're going to squish them all together in the same bucket. And we're going to lose some of the information that's present in the audio file. So that's how we go from quite a large WAV file to quite a small MP4 file. And well, that's basically my talk, which I don't know how illuminating that was, but I think one of the interesting things about audio is certainly going from that to the thing here. Does anyone have any questions? What slide should I leave it on? Shall I leave it on this one?
Right. Good. Thank you, Alan.
You're welcome. All right.
I was chatting about when we turned up with Dave was that I think JavaScript touches on a lot of things. You know, you've got the web, you've got back-end stuff, you know, and JavaScript can be used in a lot of different domains. So you know, that's why I think it's interesting to get JavaScript adjacent talks just to get an intro, because I think a lot of people in the room might be experts in stuff that they are using in JavaScript. So that's why I kind of wanted to do that, and Alan has decided to bless us with his lovely slides. Cool. Now we will move on to talk about audio using JavaScript and Ross. So welcome, Ross.
Thank you very much. Alan, just before we start, do you need to fiddle with the mic that I've got? No, we're good? Great. OK, let me get rid of this, if I can. Where's the cursor? OK. I'm glad I'm not trying to live code on this. I did consider it. OK, let's see how we go from here. Right, hello everyone. Thank you very much for coming. It's a rainy night. Good to see a lot of you here. So I'm Ross McKelvey. I'm a software engineer and security professional. I work for myself. You can hire me, looking for contracts and roles at the moment. So you can have a look at my company website to see some of the things that I do. That's my LinkedIn profile. So today, I am here to talk to you about the magic of web audio in the browser. And I am here to convince you that perhaps if your JavaScript career is not working out, you could in fact become a house music producer without any expensive equipment at all. All you need is a browser and some JavaScript. So I'm going to talk to you a bit about what web audio is. We're going to talk through some basics, then we're going to get into synthesizing some instruments, and we're actually going to make our very own house track. So what is web audio? So web audio is an API that's in every browser, and it's designed for creating and manipulating sounds. So if you're doing anything with audio that is anything beyond just playing back a clip, web audio is totally where it's at. So there's a draft specification put together in 2011. by the World Wide Web Consortium. That became a recommendation in 2021, so that was officially published. I've been working with it since about 2020, and I would say I've noticed cross-browser compatibility really improving kind of in that time. So I would say it's a really kind of solid API that you can use now. Now, you'll notice I've talked a lot about browsers, and that's because it exists in the browser. So if there are any back-end JavaScripters here, so there is no web audio support native to Node.js. However, I'm coding in Rust at the moment, and I did spot that somebody has implemented web audio in Rust for back-end use, and somebody else has written some Node bindings to it. So with a caveat that I've never used it, there is a back-end that exists and that you might be able to use should you wish. Now, why did I get into web audio? So let me tell you the story. I was building a training simulator. Let me see if I can bring this across. Oh, excuse me a second. Thank you, PowerPoint. There we go. Sorry, I normally use FreeBSD, but I needed Bluetooth connectivity today. So I'm on Windows. That was not the browser window that I wanted to bring across. Nor was that. Finally, here we go. Okay, so I was building a training simulator. So this is for people who work in security control rooms, and I was trying to make them better at responding to terrorist attack. And so there are quite a lot of important things they need to do in that, but two of the very important things are making public announcements. So if I can grab my microphone. So here we go. Mr. Skinner to the manager's office, Mr. Skinner. So a lot of these people actually don't make announcements as part of their job. So it's important for atmosphere, but it's also important for them to hear what their announcements sound like. So I might need a bit more volume. Mr. Skinner to the manager's office, Mr. Skinner. Okay, so I hope you agree that sounds a bit more like an announcement, like as you might hear it. So that's all with web audio. That's using reverb, and I've used a similar approach for radio transmissions. Echo Hotel 1, receiving Juliet Hotel, over. And similarly, Echo Hotel 1, receiving Juliet Hotel, over. So again, for these guys, communicating properly on the radio is really important, but obviously things get a bit muffled, so important to simulate that too. And again, that's all with web audio. So this app's actually written in Elm. Any of you who saw my presentation back in May, those who haven't, it's on YouTube, very welcome to watch it. So, when's PowerPoint? One of the things when you need it. I miss keyboards. This keyboard navigation. Right, so before we jump into some code, let's talk about the key concepts associated with web audio. So web audio has what it calls audio nodes. So what I want you to imagine these as are little boxes. They might have connectors on just one end, they might have connectors on both ends, but they're little boxes. And these come in three flavors. So you get some little boxes that are source audio nodes. So they would generate sound, or they might also kind of wrap a stream from somewhere else. So they might be your interface from an HTML audio element, or from like a WebRTC stream, or indeed for the microphone, which is what you've just seen there. So the second flavor of audio nodes are your effect nodes. So they take some data in on one side, they do something with it on the middle, and they spit it out the other end. So some examples of that might be, so there's a convolver node, so the kind of reverb that you heard with the announcement there. So that's an effect node. A very simple one would be a gain node. We'll see those in a minute. So those deal with amplifying the sound or indeed scaling it down. In web audio, there's so much. There's like a panner node, which you can use for spatial effects. So you can imagine if you're using audio for gaming, you might want to change the sound depending on kind of where the player was in the environment. So that's where that would be useful. And there's also destination nodes, which are, as they say, so that's where your audio goes. So for the most part, that's going to be the speakers. In my case, this Bluetooth speaker I've got sitting on the ground here. But it could also be, could be a media recorder, so you could spit some audio out. So again, in the demo, that's what I'm doing there, recording to an audio file. Or it could be a stream, so if you were streaming across a network using WebRTC. Now, before we go any further, I should warn you that audio processing, and particularly synthesizing instruments, it's a big deal, right? People make whole careers out of this stuff. I'm a software engineer. I'm not a music producer. I've no formal background in audio processing, so I will do my best to use the correct terminology. But if anybody has that background and spots me saying something incorrect, just please forgive me. So hello web audio. Let's have a look. Let's have a look at some code. So where's my browser gone? Okay. This feels painful. Right. Hello web audio. Okay, so here is my app. The demo code is available on GitHub. I've pinged the link in Discord if you're all in Discord. So let me hit go. Wow, there we go. Hello web audio. So let's have a look at the code that's sitting behind that. If I bring this over here. Okay, check that is the right one. Right, it is. So let's look at the important stuff. So before you can do anything with web audio, you need an audio context. So that's the crucial element. However, we are in a browser, and there is already a gotcha on getting your audio context. So you can have it, but if you instantiate it before the user has interacted with your page, then you don't really have it. It gets created in a suspended state. So it's to do with autoplay rules. If any of you've battled with autoplay, when you really want to kind of play some audio to your user, but you can't until they've done something on your page. So you've got two options here. So one is to create your audio context. Your browser will helpfully spit out a warning into the console saying, oh, well, I haven't actually started that yet. And then you can call this resume function on it. But given that you're going to need to run some code when your user does something on your page, you might as well just instantiate the object inside whatever's happening there. So from my examples going forward, that's what I'll do. So no more instantiating outside. So we've got our audio context. We then create a source node. So in this case, I've created an oscillator using a factory method. Could everybody see the code, by the way? I am aware that code on screen can be a bit frustrating. I tried to go big. Now, creating it is not good enough. As we talked about, you've got to connect it. So I'm connecting it to the destination, which in this case is the speakers on my laptop. So if you're thinking little boxes, I've created my context. Within that, I've got my little box, which is my oscillator, and I've connected that straight to the destination. And then so we start the oscillator, and actually that would just keep going, but I've also scheduled it to stop. So I've said when 1.5 seconds beyond the time that we're at the moment, web audio has its own very accurate internal clock. That's when we're going to stop. So let there be sound, and so it was done. So let's talk a little bit more about oscillators. That's not on the right window. Okay, let's see if we can get some code up at the same time. So, hello, oscillators. So, Alan very kindly has done a little bit of my job for me. I'm sorry, this is very painful trying to switch between stuff. Okay, so out of the box, we've got a few different types of oscillators. So this represents kind of time and amplitude of the waveform like Alan was talking about. So these are the different ones that come out of the box. Probably what's more important is what they sound like. If I can bring it up, goodness. Right, so we've got, so sine wave we've already heard. Oh, there we go, let's actually initialize our web audio. That's a bit painfully loud. But we can also, this is going to be very brash, this one. Yeah, there we go, nice. Sawtooth quite buzzy, and a triangle kind of a little bit softer. So the reason I'm showing you these is because we can use these as the basis for synthesizing instruments. Now, if we can pop and look at the code, oscillators. Okay, so we've got, you've seen the page. Where's my play sound function? Here we go. So I'm creating my oscillator, and then I'm setting the frequency. And I'm also setting the waveform. Now, and as you've seen, I'm connecting it up. So I've got my little box. I'm connecting it up to the destination. Then I'm going to start it and schedule it to stop. Now, some of the so oscillators are pretty simple. The bit of interest is the frequency. So this is something in web audio terms is called an audio parameter, which is an audio param object. The reason I draw attention to this is because these can actually change over time, which we will come back to later when we're creating some instruments. Now, another type of okay, so another type of audio source in web audio available to us are buffers. So buffers are what they store basically an array of values. So if you think back to what Alan was talking about his kind of uncompressed audio basically being a list of the kind of the amplitude of the sound as over time, that's what the buffers store. So I'm just going to, for time, I think I'm just going to slightly skip over this, but you can create a buffer in the same way that you create an oscillator, and you can fill it with whatever you want, including decoding audio data into it. So if you had an audio file, you could decode the data out by magic. You don't even need to care what formats it's in, as long as your browser supports it, and that will then appear in a buffer for you to use within web audio as a source. So I will show you some more code on that later. But in this example, just trust me that I've, in the background there, I've just filled it with a sine wave. Let's stop that one before that gets annoying. Okay, so you are thinking at this point, you're thinking, well, hang on, he promised me house music, but so far we've listened to some beeps. So if I were you, I'd probably be feeling a little bit underwhelmed at the moment. But never fear, because we are about to dive in to audio synthesis 101. Didn't have to go back to the start. Right. So let me, before we look at code, let me talk to you briefly about a method that people use for synthesizing instruments. So what you can do is you can control the amplitude of your sound wave, and that will change how it sounds, and we'll see that in just a moment. So a common way of doing it is with this ADSR curve. You hear it called an envelope. I've watched a number of YouTube tutorials over the past little while, links at the end. So what we're going to do is we're going to take our source, so imagine our source box here, so whatever that contains, and we're going to attach to that, we're going to attach a gain node, which is a type of effect, and we're going to use that to control, effectively to control the volume of the sound wave very quickly over time. And we can define that in various stages. So we talk about the attack, so that's the time it takes to reach maximum volume. You then talk about the decay, which is the length of time it takes to reach the value, which is called the sustain. And then you have the release, which is when it returns to 0. So we're going to be looking at some figures, and you just need to kind of keep this kind of vague curve in mind. Like if you had a keyboard and you press the key, this stuff happens when you first press it. The sustain would happen if you hold your finger on the key, and then the release happens when you let go. We also don't have a real keyboard, so my one is just a kind of simple attack decay and then release. So here we go. Let's get rid of that. Thank you, Windows. So do we, wary of asking for volunteers, do we have any beatboxers in the room? Okay, is somebody, Jamie? You're a beatboxer?
Yes.
Excellent. Okay, good. Well, we're all looking for alternate careers. So could you give me kind of what a kick drum might sound like? Yeah, good. That's good, actually. That's good. Okay, so a kick drum. So if you think about a drum kit, a kick drum is the big one that people typically use with a foot pedal. It goes bish. It's big, and it makes a big noise. So when you think about, so let me first of all say, we could just use a sample, right? So if we were actually making real house music, we could record a real kick drum, and we could use that in our music. That would be really sensible. But where's the fun, right? We're coders, we're developers. We can make our own drums. So that's what we're going to do. So if you think about what a drum is, you've got it's basically you've got a surface held taut. You hit it, and it kind of goes, and then it vibrates back and forth. And so what that makes me think of is an oscillator, which we've just seen. So Alan covered briefly kind of sound science. For those of you for whom it was a while doing kind of like high school science, sound is vibrations through the air, so waves passing through the air. So they come from a source and they hit your eardrum, which then vibrates, and that's how you hear the sound. So we're going to do that. So if I fire this up, let's see if I can show you in the background what's going on. Okay, so from, let's get the kick drum. Okay, so from a single oscillator, I'm confident that we can build a sensible drum. So what I'm doing here is I am creating my oscillator. I'm creating a gain node, setting the frequency. What I'm actually going to do here, so this line here, I talked about frequency as a parameter that you can change over time. So I'm using this function that's built in to web audio, and I'm actually going to reduce the frequency very fast of the drum. So you'll hear that in a minute. Connecting everything up, so I've got my source, I'm connecting that to my gain node. My gain node's getting connected to my destination. Now, I've also made this ADSR class, that's mine. Is it worth showing you? I don't think it's worth showing you. What that does is that basically ramps the gain kind of up and down again according to that curve. So I'm basically using, there's a function called linear ramp to value at time. So I'm linearly ramping up to the attack, and then linearly ramp down in the decay phase, and then I'm exponentially ramping down in the release phase. I hope I haven't just lost everybody there. But let's hear how it sounds, and that might make a bit more sense. If I can get it back. Right, so let me mess with some of these a little bit first. So if I put this back up to 440, Okay, and I'm going to have a really long decay. Okay, so you can hear I'm starting at a frequency and I'm ramping downwards, but that's not really sounding kind of like a drum yet. But if I, and indeed if I were to slow the attack as well, that's going to sound even less like a drum. So remember, we've just got a single oscillator here. Okay, so there we go. So there's our sound, but it doesn't really sound like a drum yet. But if I were to drop the attack back, in fact, let me, do you know, I'm just going to totally cheat here and reset to the values that I had earlier, if I can force a refresh. Come on, Windows. There we go, okay. Ooh, so I'm hoping that you can kind of, that's a believable drum. So we've gone from a single node, oscillator node. That's a little bit higher, doesn't really sound like a drum there. But we've gone to something that sounds passably like a kick drum. Yeah, cool. Okay, so what else can we do? Well, we can make a hi-hat. So if anybody hasn't seen a hi-hat in the drum kit, it's where you've got like two cymbals. They sit on a kind of stick. You can tell I'm not a drummer. They can be open or closed. They make noise. So beatboxer volunteer. There's no shame. Left shame at the door. Jamie's volunteering again. Can you make a noise? Okay, that's good. Perfect, right? So what's interesting? No, absolutely not. So what's interesting there is it's not really like an oscillator, right? We're kind of listening to our waves there. It doesn't really sound like that. But do you know what it sounds to me like? It sounds to me quite like white noise. Now, that is a perfect time for when to use a buffer. So let's have a look at our hi-hat. Hi-hat, here we go. Okay, so we've got our audio context. So what I'm going to do is I'm going to build a buffer. So let me show you my code that's building a buffer. Here we go. So, okay, so I'm using my audio context to create a buffer. This code here is basically about calculating how big I need that buffer to be. So I'm saying, well, it's this many samples and I want this many seconds of it, and so that's good. So I have to supply that when I'm creating it. As I say, web audio, you can do all sorts of stuff with multiple channels, stereo, Dolby, whatever. We're not doing that today. So in this function here, I fill it. So I'm basically just looping through all the elements in the buffer. And the nature of white noise is it's just random values. So that's what we've got. Very, very simple buffer. So the buffer you create once, you can use it multiple times. The sources you can only use once. So you use them once and they're burned. You have to discard them and go again. But a white noise on its own is not really going to cut the mustard, and I will play you a sample of that in a minute. So what I'm using is I'm using a filter, so you can see this biquad filter node. So this is one of those effect nodes. So I'm going to use a filter to really narrow down the frequencies that I'm bringing down from that hi-hat. So if I pop back to my web page, where's my hi-hat page? Here we go. Right, so, okay, so if I make my filter, I'm just going to make my filter very wide. Okay, so that's quite white noisy, and it will get even more white noisy if I were to extend the attack or something. Okay, so that's very, very much not a hi-hat at the moment, but if I were to do this, so the values up here, filters, they have two parameters, so one, or this type of filter anyway, there are lots of different types of filters. This one, if you imagine you've got your your frequency graph that Alan showed you, and what you do is you basically say, right, I'm gonna take a cone, I'm gonna place that somewhere, and where you place that is on that filter frequency, and this Q value is basically a measure of how wide it is. So if I put that up at 20, I think I had it, that would be quite a lot narrower. Okay, that's now quite quiet because we've lost quite a lot of the sound. because I've kind of filtered it out. But can you hear that, everybody? Okay, so to me, that sounds a bit more like a convincing hi-hat. So there we go. So two instruments down, one to go. So next up, we have what we're going to use for our riff. Now, here we go again. So we're going to be using oscillators to build ourselves an instrument. So if you think about real instruments, like they don't sound like the sounds that I've just played you here. Like they don't sound like any of the waveforms. And the reason for that is that they're much more complex. So they would contain like a range of harmonics and some that are kind of on and some that are slightly detuned, whatever. So what we need to do is we need to make a slightly better instrument by increasing the number of oscillators that we use. So what I've done here, where's my riff synth? Here we go. So I've got my oscillators again. I've chosen a triangle waveform. There's my ADSR curve. Right, but rather than just using one oscillator, if you can see the code here, what I'm actually doing is I'm creating 8 oscillators. So I'm going to create 8. I'm going to set the frequency so that so you've got your base frequency, and then I've got 8, and they've each got kind of double the frequency. They've all got their own gain nodes, and I'm kind of slightly reducing the gain as you get kind of higher frequencies. So this is just a very, very simple synthesized instrument, but you'll see it actually adds, even such a simple instrument actually adds quite a lot of depth to the sound. So if I'm going to go totally Blue Peter and say, here's one I made earlier. Okay, so here's our sound, and we can change the pitch of the notes by changing the frequency. Here we go. So we're just about good to go. Now I've actually also made another instrument. I've made a bass instrument, which I've basically just reused my riff synth for, but with a different oscillator type. So let's make some music. Okay. So okay, so we're initializing our audio context, and behind here I've written a very basic scheduler. Happy to talk about it. For time, I will not. But if you want to ask me about it in the questions, I can talk a little bit about that. So let's start. So let's take off some of the instruments. So what lies behind here are two bars, and that is it. 2 bars of arrangements of the different instruments, and hopefully you will suddenly hear that that's actually sounding like music. Like, who would have thought that we could go from those crazy beeps to something that would sound like music? Here's our hi-hat. A little bit quiet. Okay, let's bring in the bass. Oh, slightly late on the uptake there. Okay, so what I've got is I've got multiple of those synth instruments that we created, because then I can use them in chords. So they'll be in chords with this bass drum. Here we go. So I'll bring these 2 on, so you can kind of hear them, right? So they're not very impressive on their own, but you put them together, and then suddenly we can bring in a little riff over the top. I bring you deep house in JavaScript. And with only 2 bars, we can still do quite a lot. So we can take some of this stuff out. Oh my goodness, there we go. That almost sounds like something you'd hear on Spotify. Okay, and there we go. Okay, let's take that off. Okay. There we go, we'll just bring that to a stop. So, music in JavaScript. Let's get all the way through. Oh, no, past the end. So, there we go. So, thank you very much. I'm Ross McKelvey. Thank you, good applause, thank you. So demo code is here. You can have a look at it. As you will see from my beautiful styling, I've not used any kind of frameworks or anything like that, so it's just pure JavaScript. MDN has some absolutely great web audio tutorials if you're interested. Here are some notable libraries that if you just want to play, they will take some of the pain away. BBC have actually put together some React components. I know we've got quite a lot of React developers here, so you can put them out declaratively rather than having to muck about with JavaScript. And there's the link for the Rust backend, should you wish to look at it.
Cool. Thank you very much, Ross. That was actually excellent. Does anybody have any questions about oscillators and so on?
Hello.
Dave. Speaking that for YouTube.
Hi. Is
That's
it,
for
no,
the-
that's for them, right? Okay. No, so are there any open source tools that do similar functionality to tools like Sigma DSP? If you've come across Sigma DSP.
I've not come across Sigma DSP.
Okay. Sigma DSP is a graphical development environment for audio DSPs.
Okay.
So basically, you take all the blocks and the filters and you place them graphically and join them
Yeah,
up.
I know
And-
that. So I know the type of thing that you're seeing. Do you know? I've seen some people have put together some stunning web applications that would come close to doing stuff like that. I don't think they'll be as good. I mean, as I say, you saw what I was using this stuff for. So putting together the sequencing and stuff. I mean, if that was your aim, I don't think JavaScript's really where you want to be, right? You'd want to be doing that at the back end to, on your desktop, produce a nice song and put it out.
As a toy, so to speak.
As a toy.
You know, to explore the API,
Yeah.
to grab filters and play with the parameters and join them up and basically graphically do similar to what you've done.
Yeah, I mean, so I've certainly come across so somebody recreated a Roland drum machine, I think, again using web audio. Oh, was it? Okay, there we go. Oh, thank you. But I'm sorry, not my area, so I can't recommend something on the desktop.
Anybody else?
I was just in answer to Dave's thing. There's a JavaScript implementation of something called pure data. So if you try looking for JavaScript pure data, you might find something which is similar.
Yeah.
Pure data is a cheap version of Massive, I think it's called, the DSP software. So
Yeah,
I can't remember what it's called though.
what I would say is, I mean, I know we kind of flashed through the code there, but there's really not a lot going on. Even coding straight on top of the API, it's amazing how much you can do with really very, very little.
Cool. Anybody else?
Thank you. Thanks for the presentation. It was great. Just wanted to understand the memory constraints which you have to
Yes.
play with because it's in a browser and obviously audio
Yep.
files and everything is like pretty heavy. So what are the limitations that we are working with here?
Okay, so actually it's pretty good. Even on mobile, web audio is pretty good. As a coder, you need to be a little bit careful. So, so the audio nodes, you need to make sure that they can be garbage collected. So if you have a look at some of my demo code, so for example, the synth instrument I was creating, right? So every time, I think I was reusing my gain nodes for some of that, but I was potentially creating a lot of nodes very, very quickly. And if you don't disconnect those, then they sit in memory. Whereas if you disconnect them, they'll get garbage collected. Specifically on audio samples, so the recommendation on bringing things into buffers is that you should really limit that to about a minute's worth of audio. You can play direct from like audio elements, HTML audio elements, and streams, excuse me. What you lose with that is you lose control over the timing. So the stuff that I showed you first of all, like with the radio and the public announcement, being like, if it's a third of a second out, doesn't really matter. If your bass drums have a third of a second out, you're really going to hear it. What I would say is that I'd worry less about memory and probably more about computational performance. So again, recommendation, because there are all sorts of nodes, particularly effects nodes in web audio, but you can actually write your own, and you can write your own in JavaScript. Now, to my mind, JavaScript has many qualities. A good real-time language, it is not. So, but what you can do is you can write in Rust or C, and then bring that in, bring a component in via WebAssembly, and then you've got the performance as well.
Any more questions? Oh, sorry.
I hate to be the ruthless capitalist and ask about the commercial side of things here, like the applications you could use it for. But I've often thought about creating some kind of podcast editing app in the browser. Do you think it would be more optimal to use something like this, or to run it, on a server, make the request, do it in that, and then bring it back? What would you do if you were in my shoes? Because I'm now very keen to build it with this because this is really cool.
The length of the clips I could see becoming an issue. You might need to do something about splitting them. I think you'd be all right. Yeah, I can see that working. I can see that working. I mean, particularly if you were to keep stuff broadly out of memory. So if you have it in like audio elements, like files that can be brought down. So I mean, when I was putting that simulator together, my expectation was that I was going to have to fire off to the back end to do anything sensible with audio, and I was really, really, very, very pleasantly surprised. I mean, this is all. You're obviously instantiating objects, but they're all implemented in native code in the browser, so they are quick. They'll be running, almost like a native app on the machine. I'd have said that's not a ridiculous idea.
Okay, cool. No, might give it a try. I'll let you know if I do.
Yeah, for sure.
Cool. Anybody else?
So obviously this is like geared at web audio. Have you ever actually tried to code like a plugin for a DAW or something like Logic or Ableton or something like that?
So a plugin for
like a digital audio workspace, like that you would use to like record tracks.
Have I tried to code one? No. So
Yeah.
I mean, so you saw what I had coded, which was somebody speaking into a microphone, and and that gets recorded and sent back to the server, as well as being available locally. That app actually also it's got a telephone, a simulated telephone that you can use, and you can actually talk into it as if you're talking to a real person, and it will detect when you're talking and when you're not. And it's actually surprisingly convincing, as if you're having a conversation. But no, specifically what you're asking, no.
Cool. If there's no one else, thank you, Ross,
Cool,
for
thank you.
that. Just a couple of housekeeping things. So firstly, the draw for Quokka.js and Wallaby.js, thank you very much to them for providing licenses. Dale, Quokka.js license for you. And who is Stephen with PH? Yep. Is that you? You've got a Quokka and a Wallaby.js license. So message me after and I will send you the details so you'll be able to claim them. If you're dead interested in what that is, we'll be doing the same again next time. So if you've missed out, this isn't your last chance. So if anybody wants the code and stuff, Russ has got the links there. I run a Discord server, scottishtechnology.club. That's basically me summarizing the events that are on in Scotland every week, and people can ask questions. That is kind of very low key, but it's the way that I'm using it to communicate with people. So feel free to join that, and Ross has posted his code there. Next time, we will be back here in October with a talk from Harvey, who works here at FanDuel, who will be talking about building kind of SDKs, libraries, that kind of thing. And Russell, who I haven't spoken to yet, and I'm assuming you're the Russell I'm speaking to online, talking about Chrome extensions, hopefully, if we can arrange the date. So that will be next time. Keep an eye on the Meetup group for the announcement for that. Thank you for coming tonight. There's a little bit of pizza left and a few beers left in the fridge. And if you eat and drink, then that means I don't have to lug them away tomorrow. So please help yourself. Thank you for coming, and see you next time. Cheers.